Have you ever played with a toy magnet and noticed how it sticks to your refrigerator? Or how it magically repels another magnet when you flip it around? What you were holding was most likely a bar magnet, one of the simplest yet most powerful tools in understanding magnetism. A bar magnet is a rectangular piece of material that permanently possesses magnetic properties. It has two distinct ends, the North Pole and the South Pole, where its magnetic power is most concentrated. Just like electric charges, magnetic poles obey a simple rule, like poles repel and unlike poles attract. Now, even though the magnet itself appears passive, it's always at work. It creates an invisible magnetic field around it, an active zone that can attract other magnetic materials or even deflect compass needles. As you can see in the diagram, this field isn't random, it follows a structured pattern, which we'll explore next. This pattern is key to understanding how magnets interact with other objects and how their influence spreads out in space. So, the next time you feel that invisible force pulling or pushing, you'll know it's the magnetic field doing its work, quietly but powerfully shaping the world around us. Have you ever used a magnet to stick notes on your refrigerator? Or seen how large cranes lift heavy metal objects with just the power of a magnet? These are all real-world examples of how magnetic fields work. But have you ever wondered how these invisible forces actually function? Magnetic field lines are imaginary lines that help us visualize and understand the direction and strength of a magnetic field. These lines emerge from the north pole of a magnet and curve around to enter the south pole, forming a closed loop. Inside the magnet, the field lines travel from the south pole back to the north pole, completing the loop. What's fascinating is that the field is strongest near the poles, where the field lines are closest together. Imagine the poles as being like the busiest spots in a stadium, where the crowd is densest. As you move farther away, the field lines spread out and the field weakens. So, magnetic field lines give us a way to visualize how the magnetic force flows. They guide us in understanding how magnets work in everything from holding up a picture frame to helping us navigate with compasses. These invisible lines play a huge role in our everyday lives, and the more we understand them, the more we can appreciate their power. Have you ever noticed how a simple bar magnet, though small, can control metallic objects around it with ease? What's interesting is that in physics, we treat a bar magnet as something called a magnetic dipole. Why? Because it has two distinct poles, a north and a south, separated by a certain distance. To measure the strength of this dipole, we use something called the magnetic dipole moment, denoted by M. It tells us how strong the magnet is and in which direction it acts. The formula is M equals M multiplied by 2L, where M is the pole strength and 2L is the distance between the poles. Now, this dipole moment is not just a number. It's actually a vector, which means it has both size and direction. And interestingly, its direction is always taken from the south pole to the north pole of the magnet. In terms of units, we measure it in ampere meter squared. That's a meter squared. This unit represents both the magnitude and the orientation of the magnetic strength. So, in simple terms, every bar magnet can be thought of as a tiny magnetic dipole, with its strength neatly captured in the idea of the dipole moment. And this simple idea helps us link the everyday bar magnet to the much deeper physics of electromagnetism and even the Earth's own magnetic field. Imagine placing a bar magnet in an open field of invisible lines. What happens? The magnet doesn't just sit quietly. Instead, it experiences a twist or torque that tries to turn it so it lines up with the magnetic field. This is nature's way of ensuring order. The magnet always wants to align itself with the field. Now, what decides how much torque acts on the magnet? It depends on two things. First, the magnetic dipole moment of the magnet itself, and second, the strength of the magnetic field. The relationship is beautifully captured in a simple formula, tau equals mb sine theta. Let me spell that out. Torque tau is equal to magnetic moment m multiplied by magnetic field B multiplied by sine of theta, where theta is the angle between the dipole moment and the field. As you can see in the diagram, when the magnet makes an angle with the field, a restoring torque acts to bring it into alignment. The effect is maximum when the magnet is exactly perpendicular to the field. That's when sine theta equals 1. And the torque becomes 0 when the magnet is already parallel to the field because sine theta is 0. This principle is not just theory, it's what governs how compasses work. The Earth's magnetic field applies this torque on the compass needle, making it align north-south. It's the same idea applied on a planetary scale. So, to sum up, a magnet in a uniform magnetic field experiences a torque given by tau equals mb sine theta, with the torque strongest at right angles and vanishing when parallel. It's a simple but powerful idea that explains both the compass in your hand and the alignment of magnetic materials in technology around us. I hope this helps you see magnets not as static objects, but as dynamic dipoles that constantly interact with the invisible fabric of magnetic fields. In the next session, we'll uncover more about how these interactions drive real-world devices. Have you ever tried to balance a pen upright on your desk? For a moment, it stands tall, but then it quickly tips over to settle flat on the table. Why does this happen? It's because systems in nature tend to move toward lower energy states, a position of stability. A bar magnet in a magnetic field behaves in the very same way. The potential energy of a magnet in a uniform magnetic field depends entirely on its orientation. Mathematically, we describe this using the formula U equals minus m into b cos theta. Let me spell it out. Potential energy U is equal to negative magnetic moment m multiplied by magnetic field B multiplied by cosine of the angle theta between them. What does this mean in simple terms? When the magnet aligns with the field, the angle is 0, cosine theta is 1, and the energy is minimum. This is the most stable position, just like the pen lying flat on your desk. But when the magnet is anti-aligned, pointing opposite to the field, the energy is maximum and the magnet becomes unstable, like trying to balance the pen upright. As you can see in the graph, energy dips to its lowest when the magnet is aligned and rises when it is turned against the field. This is why magnets naturally settle in stable orientations. Nature always prefers the path of least energy. So, to sum up, the concept of magnetic potential energy not only helps us understand how magnets behave in a field but also shows us a deeper truth of physics. Systems always seek stability by minimizing energy. I hope this gives you a clear picture of why magnets choose their orientation. In our next lesson, we'll explore how this idea links to real-world technologies, from electric motors to data storage devices. Have you ever noticed how the strength of a magnet seems much greater when you bring a nail close to its ends, but weaker when you move farther away? That's because the magnetic field created by a bar magnet is not the same everywhere. It changes with distance and direction. Now, let's understand this scientifically. The magnetic field due to a bar magnet varies depending on whether you are along its axis or along its equatorial line. On the axial line, which is along the length of the magnet, the field is stronger. The formula is B axial equals mu naught divided by 4 pi multiplied by 2m over r cubed. Here, m is the magnetic dipole moment and r is the distance from the center of the magnet. On the equatorial line, which is perpendicular to the magnet's length, the field is weaker. The formula is B equatorial equals mu naught divided by 4 pi multiplied by m over r cubed. As you can see in the diagram, the axial and equatorial field directions differ, but in both cases, the strength falls very rapidly with distance. In fact, it decreases with the cube of the distance. That means if you double the distance, the field strength reduces to just 1/8. This idea not only explains why the ends of a bar magnet feel stronger than the sides but also forms the foundation of how magnetic dipoles behave in real-world physics, from the way compasses work to the modeling of Earth's magnetic field itself. So, to sum up, along the axis, the field is twice as strong as compared to the equatorial line, and in both cases, it weakens sharply with distance. A simple yet powerful idea that tells us how magnetic influence spreads through space. Let's take a moment to bring everything together about the bar magnet. A bar magnet, as we've seen, has two poles, north and south, and it behaves just like a magnetic dipole. From its north pole, magnetic field lines emerge and they curve around to enter at the south pole, forming continuous closed loops both outside and inside the magnet. We also learned that the magnetic dipole moment plays a central role. It not only determines the strength of the magnet but also governs the torque and the potential energy when the magnet interacts with a magnetic field. Another key idea is about distance. The magnetic field produced by a bar magnet decreases very rapidly as you move away. Specifically, it reduces with the cube of the distance. That's why magnets feel powerful when they're close, but their effect weakens quickly as you move farther away. So, to sum up, the bar magnet is not just a simple classroom object. It's a tiny dipole that demonstrates the deep principles of magnetism: poles, field lines, dipole moment, torque, energy, and the sharp fall-off of field strength with distance. I hope this summary has given you a clear and connected picture of how bar magnets work. In our next session, we'll extend these ideas to see how they apply in larger systems, including the Earth's own magnetic field.